Hello and welcome to today's mini test solving, lecture 31, real-world differential equations. As opposed to other mini tests, we will focus more on the understanding the problem rather than doing the math, which you can still do, of course. But if you understand the question, the system and the formula, if you know all of these three, it makes solving mathematically a lot easier, basically. This is the mini test for those of you who came here just to solve it. And let's get right ahead into the first one. So this one is easy. We can either go and think deeply about how temperature changes, but the key word is cooling, which means temperature decreases. So which of these three changes signifies a decrease? Does the square change decrease? So if the change of a system is square, so as time increases, temperature is exponentially objectively higher? No, because decreasing means it should be lower. Does this one do that? No, because it involves only the temp, like, it's a positive term. If it was k times delta t, it could be correct, because it depends on how we would define this delta t. So which were our conditions. So this one, unfortunately, is not correct as well. If it was delta t, it could be correct. This one, however, has a minus and a delta. So no matter what it is, it best models cooling of the hot object out of all of these three, especially because the cooling is dependent on the change of temperature, the difference between two temperatures. And I mean, this is the main part. If you know it, that's perfect. If you don't, then this minus is the second part. So if you find either of these two as a cause or explanation, it should be correct, at least in this mini test. So hopefully this was clear why exactly this change of temperature, more on that in thermodynamics. So for the next question, we know that a certain object in free fall will eventually stop accelerating. The question is why? Now we know that that happens when it reaches its terminal velocity. That's one of the situations. But which of the three given causes would cause that? Sure, I could just write the question and let you answer it, but I was feeling kind when making this mini test, so I gave you three different options. So for the first one, we know it's just wrong because gravity doesn't disappear, especially not in free fall. If anything, the acceleration itself would have increased because, well, in physics we'll learn that the gravitational acceleration is the force of gravity kind of depends on how far you are from the core, and we will be able to calculate the difference between such accelerations, but more on that in physics, yeah. So we know the first one is incorrect. Now for the second, when air resistance balances gravity. Now I do not like the wording. It states that, basically it just states that the two forces, the accelerating and decelerating force, are equal and opposite, so they cancel out. That means that there is no more acceleration, which makes this option correct. Now for the third one, is it correct? Is it not correct? It should not be correct, right? Well, in a free fall, technically you're falling, but the question asks about eventual stop of acceleration. Acceleration stops when the velocity is either constant. Yeah, I wouldn't write it as a k, but constant. I could write as k. This is the first situation for eventually stop to accelerate. The second one is when velocity is 0 and it doesn't change, so it's also a constant. So the first one is a non-zero constant and the second one is 0 constant. But when does that happen? Does that happen during a free fall? Well, yeah. If we imagine a stickman jumping off of a cliff, when the stickman splatters onto the ground, its velocity downwards is 0. Therefore, technically, this answer is also correct, as you do stop moving if you hit the ground, as grim and dark as that sounds. Technically, the acceleration stops. This is one of the reasons why acceleration would stop. Although, if you would look at the graph, the acceleration downwards is pretty much consistent. Then there's like a drag that increases, and at some point you just get smacked into the ground with a huge force pointing backwards, and after that they're all gone. So yes, B is the most correct and sought after answer. C is technically correct, but it's not the best one. But it's just like a small trick that I added to the question. As for the third problem, we are given the following differential equation. We know that the drag increases and mass stays the same. So what happens to terminal velocity? Now, I'm not doing the entire thing we did in the lecture. For that you can check the lecture itself, but I will use common sense on how we can solve this faster. So the orange part represents the rate of change of velocity. Terminal velocity is when the velocity isn't changing anymore, therefore that part would equal to 0. Since now that the rate of change is 0, we either have terminal velocity or a stationary object. Since the latter has velocity of 0, we will change the marking of velocity, or v, into v terminal and then isolate it. So we move this entire term to the left, and now we just divide by the drag coefficient, and this is our formula for terminal velocity. Now let's move the constants outside the fraction so we can get a sort of k times x function, where x is another subfunction with all the new variables we have. So first of all, g. We know that the gravitational acceleration is a constant. There is no question about it, so we can move it out of the fraction. For ease of, so like we can say velocity is dependent on some x, and we're determining what that x is. So next up is mass. The title says that mass stays the same, so we can treat it as a constant. Well, technically you shouldn't be losing weight while falling that fast, but who am I to judge? So these are our constants. Now, what about b, the drag coefficient? I have said that it is a constant, however, it does represent drag. Because this quote-unquote constant combines stuff like the surface at the front and other parameters, it can change if you switch from a pointy rocket to a parachute, for instance. This problem would accurately describe a light particle that somehow got attached to a parachute mid-fall, even though this light particle wouldn't need it because linear law basically makes it fall super slow, basically opening up the parachute. That's it. The b increases exponentially, or exponentially significantly, while mass stays roughly the same. So in that way, b becomes our variable because it increases. But what would this mean for the overall terminal velocity? Well, it decreases proportionally to the drag increase because it's in the denominator. Let's say gm times, if the drag coefficient or whatever was 1, the terminal velocity would just be gravitational acceleration times mass. If it were 2, it would be gravitational acceleration times mass halves. So we see that the higher the b, the lower the v, kinda. But yes, that was it for today's mini test. Hopefully this lecture did show you where physics and math do actually apply in real world, like how you can use differential equations to just describe a cup of tea. And yeah, thank you so much, and I'll see you all next time. Bye!